Now let's put an equation to entropy. We've already said that entropy is, there are absolute values of entropy, and we can calculate that absolute value of entropy if we know W, where W is the number of microstates. And W is the number of energetically equivalent ways to arrange the components. Of a system. And so that's another way of saying it's the number of microstates. Now K, and this is lowercase k, so I'll draw it like a lowercase k. This is a new constant. It is called the Boltzmann constant. B-O-L-T-Z-M-A-N-N constant. So it is not the rate constant. And it is equal to R divided by Avogadro's number. Avogadro's number, where R is 8.314 joules per mole Kelvin. And you'll notice that joules per mole Kelvin is the unit that we typically see for entropy. And Avogadro's number is 6.022. And I'll use e to the 23rd here so I can fit in my units. And this is going to be, for this time, microstates per mole, or particles per mole, which microstates per mole, yep. And then we get our per mole to cancel out, and K will have the number 8.314 divided by 6.022 exponent 23rd. I get 1.38 times 10 to the minus 23rd joules per microstate Kelvin. Because this is going to be the energy per Kelvin for a microstate. So, and now we're going to look at, this is the natural log function, ln. And typically what we'll do is we will, so the first thing is we've already talked about how this microstate is more probable because there are, or so let's say this, 2 and 2, there are 6 possible microstates. And we're going to compare it just to the microstate of having 4 in one of them, so there's 1 microstate. And what we're going to do is we could calculate the entropy of each of these, but typically we're going to be interested in calculating the change in entropy, delta S. And delta S is going to be, we're going to calculate the change in entropy between this state and this one. So delta S is going to be the entropy of, let's call this state 1, or state final, actually. We'll call this state initial. So we're going to calculate final minus initial to see the entropy change in going from here to here. It's going to equal K ln 6, because there are 6 microstates, minus K ln 1. And we can then condense this to K equals ln 6 over 1, because any two things that are divided, and that gets, well, let's do the math. 6 natural log times 1.38 exponent 23rd minus equals 2.47 times 10 to the minus 23rd joules. Well, we've canceled out our microstate term here. Actually, no, we didn't. So joules per microstate Kelvin. Because any of the units, there were no units on our microstates, but whatever they were, they would have canceled. And so what we have just done is we've calculated the change in entropy as going from here to here. It is positive, and we're going to see that positive entropy changes are when things tend to happen.